The strangest objects in the universe. Picture this. Right now, at this very moment, somewhere in the depths of space, there is an object so dense that a single teaspoon of it would weigh more than every human being on Earth combined. Somewhere else, a star is spinning so fast it completes 600 rotations in a single second, warping the very fabric of space-time around it like a cosmic tornado. And in another corner of the universe, there exists a void so vast and so empty that if our entire Milky Way galaxy were placed at its center, we would see absolutely nothing in any direction for 330 million light years. Nothing. Just an incomprehensible emptiness that shouldn't exist according to everything we thought we knew about how the universe works. These aren't science fiction fantasies. These aren't the imaginings of creative writers trying to outdo each other with cosmic horror stories. These are real objects that exist in our universe right now, objects that have been observed, measured, and studied by scientists who are still struggling to fully understand what they're seeing. And here's what should truly make your spine tingle. These strange objects aren't rare exceptions scattered across the cosmos. They're everywhere. Our universe is filled with things so bizarre, so contrary to our everyday experience, that even the scientists who dedicate their entire lives to studying them still speak about them with a mixture of wonder and unease. What does it mean that we live in a universe where the strangest, most impossible seeming things are not only real but fundamental to how everything works? What does it say about reality itself when the deeper we look into the cosmos, the stranger it becomes? Let me take you on a journey through the strangest objects in the universe. A journey that will challenge everything you think you know about the nature of reality, space, and time itself. But I have to warn you, once you truly understand what's out there, you'll never look at the night sky the same way again. We begin our journey with perhaps the most famous strange object in the universe, yet also the most profoundly misunderstood: the black hole. You've heard of black holes, certainly. They've become part of our popular culture, appearing in movies and television shows, usually portrayed as cosmic vacuum cleaners that suck up everything around them. But the reality of what a black hole actually is goes so far beyond these simple descriptions that even trying to explain it properly requires us to fundamentally rethink what we mean by basic concepts like space, time, and existence itself. Imagine you're an astronaut, floating in your spacecraft, approaching a black hole. But this isn't just any black hole. This is a stellar mass black hole, the collapsed core of a star that was once perhaps 20 times more massive than our Sun. That entire star, all of its matter, has been compressed down into a space so small that it occupies literally zero volume. Not a very tiny volume. Zero. All of that mass exists at a single point called a singularity, a place where the laws of physics as we understand them simply break down and stop making sense. But you can't see the singularity itself because surrounding it is the event horizon, the point of no return. The event horizon isn't a physical surface, it's more like an invisible boundary in space, but it's a boundary unlike anything else in the universe. Cross the event horizon, and you can never, ever come back. Not with the most powerful rocket engines ever conceived. Not by moving at the speed of light. Never. The escape velocity beyond the event horizon is greater than the speed of light, and since nothing can travel faster than light, nothing can escape. Here's where it gets truly strange. As you approach the event horizon, time itself begins to behave in ways that seem impossible. To you, sitting in your spacecraft, everything seems relatively normal. Your watch ticks away seconds at the same rate it always has. But to an observer watching you from a safe distance, something horrifying is happening. You're slowing down. Your movements become more and more sluggish. Your spacecraft's engines fire in what appears to be slow motion. And as you get closer and closer to the event horizon, you slow down more and more, until, from the outside observer's perspective, you appear to freeze completely, suspended forever at the edge of the black hole, your image becoming redder and dimmer until it fades from view. But remember, from your perspective, nothing strange is happening with time at all. You simply cross the event horizon and continue falling. This is the nature of relativity, the strange truth that time itself is not absolute but depends on gravity and motion. Near a black hole, gravity is so intense that it warps time in ways that seem like they should be impossible. And here's something that should make you pause and really think. What happens to you after you cross the event horizon? This is where things become truly nightmarish. There's a process that physicists have given a darkly humorous name: spaghettification. As you fall toward the singularity, the difference in gravitational pull between your head and your feet becomes so extreme that you're stretched out like a piece of spaghetti, longer and thinner, while simultaneously being compressed from the sides. Every atom in your body is pulled apart. You're not just killed, you're disassembled at the atomic level. But here's what haunts physicists late at night. What actually happens at the singularity? We don't know. Our current theories of physics predict that density and gravity become infinite at the singularity, but infinity isn't really a physical answer. It's mathematics telling us that our theories have reached their limit, that we're missing something fundamental about how the universe works. Ask yourself this: what does it mean for something to exist at a point with zero volume? Can you even conceptualize that? We're talking about an object that has mass, that has gravity, that affects everything around it, but that doesn't occupy any space. It's not just small, it's literally dimensionless. How is that possible? The truth is, we don't know. Some physicists speculate that quantum effects, which we don't yet understand how to incorporate into our theories of gravity, might prevent the formation of true singularities. Maybe, at the very center of a black hole, matter exists in some exotic state we've never encountered before, compressed to densities where the very concept of space breaks down. Maybe. But we don't know, and here's the terrifying part: we might never be able to know. You can't observe what's inside a black hole from the outside, and you can't send information back out from the inside. The interior of a black hole might be forever beyond the reach of science. Now, let me tell you about something that sounds like it should be science fiction but isn't. Black holes aren't black. Not exactly. In the 1970s, a physicist named Stephen Hawking discovered something that shocked the scientific community. He found that black holes should emit radiation due to quantum effects near the event horizon. This Hawking radiation means that black holes actually glow very, very faintly, and over unimaginably long periods of time, they evaporate. A stellar mass black hole would take longer than the current age of the universe to evaporate, but eventually, given enough time, every black hole in the universe will disappear in a final burst of radiation. But this creates a paradox that physicists are still arguing about today: the information paradox. According to quantum mechanics, information cannot be destroyed. But if you throw something into a black hole, and the black hole eventually evaporates completely via Hawking radiation, where did the information about what you threw in go? Did it disappear? That would violate quantum mechanics. Is it encoded somehow in the Hawking radiation? How? This might sound like an abstract puzzle, but it cuts to the heart of fundamental questions about the nature of reality, about whether the universe is deterministic or not, about whether the past uniquely determines the future. And black holes get even stranger. In 2019, humanity achieved something remarkable. We took a picture of a black hole. The Event Horizon Telescope, a network of radio telescopes scattered across the Earth working together, captured an image of the supermassive black hole at the center of the galaxy Messier 87. When that image was released to the public, people around the world saw the same thing: a glowing orange ring surrounding a dark circle. That dark circle, that shadow, is the black hole's event horizon, backlit by the glowing accretion disk of superheated matter spiraling into oblivion. But here's what most people don't realize about that image. The black hole in that photograph is enormous beyond comprehension. Its event horizon is larger than our entire solar system. It contains the mass of 6.5 billion suns, all compressed according to relativity into a zero-volume singularity. How does nature create such a thing? How did 6.5 billion suns worth of matter accumulate and collapse into a single point? The honest answer is that we're not entirely sure. We know that supermassive black holes like this one exist at the centers of most large galaxies, including our own Milky Way. Our galaxy's central black hole, called Sagittarius A star, contains about 4 million solar masses. These cosmic monsters appear to play a crucial role in galaxy formation and evolution, their gravity helping to organize the motion of billions of stars, their energy output when they actively feed on matter regulating star formation throughout the galaxy. In a very real sense, these bizarre objects that seem to represent destruction and oblivion are actually fundamental to creating the organized structures we see in the universe. Think about that for a moment. You, me, everyone you know, the Earth, the Sun, all of it exists in a galaxy that is organized around and fundamentally shaped by an object so strange that it represents a breakdown in our understanding of physics. Doesn't that make you wonder what else we don't understand about the universe we live in? But as strange as black holes are, they're just the beginning. Let me introduce you to their cosmic cousins, neutron stars. If black holes represent matter pushed past the breaking point until space and time themselves collapse, neutron stars represent matter pushed right up to that edge but not quite over it. When a massive star runs out of fuel and explodes in a supernova, sometimes the core that remains is too massive to become a white dwarf but not quite massive enough to collapse into a black hole. What happens instead is that the electrons and protons in the atoms of the core are crushed together by gravity so intense that they merge into neutrons. The result is a neutron star, a ball of neutrons held together by gravity, and the density of this object is genuinely difficult for the human mind to fully grasp. Remember when I told you that a teaspoon of one of these objects would weigh more than all of humanity? I wasn't exaggerating. A neutron star packs more mass than the Sun into a sphere only about 20 kilometers across. A teaspoon of neutron star material would weigh about 4 billion tons. Let that sink in. 4 billion tons. In a teaspoon. If you could somehow bring that teaspoon to Earth, it would punch through the ground, through the crust, through the mantle, heading toward the Earth's core, nothing able to stop its descent. The gravity at the surface of a neutron star is about 200 billion times stronger than gravity on Earth. If you could somehow stand on the surface of a neutron star, which you absolutely couldn't, the gravity would instantly flatten you into a layer of atoms less than a single atom thick. The mountains on a neutron star, and they do have mountains, are no more than a few millimeters tall, because gravity is so strong that it crushes anything that tries to rise above the surface. But here's where neutron stars get truly bizarre. Many of them spin. Not just spin, but spin faster than seems possible. Pulsars, which are rotating neutron stars that emit beams of radiation from their magnetic poles, can rotate hundreds of times per second. The fastest known pulsar, called PSR J1748-2446 AD, rotates 716 times per second. 716 complete rotations every single second. The surface of this star is moving at roughly 1/4 the speed of light. Think about what that means. This is an object more massive than the Sun, denser than an atomic nucleus, spinning so fast that it completes more than 700 rotations in the time it takes you to say the word pulsar. How is this possible? How does an object not just tear itself apart at these speeds? The answer lies in the incredible strength of the neutron-degenerate matter that makes up the star. Neutron star material is the strongest material in the universe, billions of times stronger than steel. It has to be, or the star would indeed rip itself apart. And the magnetic fields around neutron stars, particularly around a special class called magnetars, are the strongest magnetic fields known to exist anywhere. A typical neutron star's magnetic field is about 1 trillion times stronger than Earth's. But magnetars are in a category all their own. A magnetar's magnetic field is up to 1,000 times stronger than a regular neutron star's field, reaching intensities of 10 to the power of 15 Gauss. To put that in perspective, if a magnetar were located halfway between the Earth and the Moon, it would strip the information from every credit card on Earth. From halfway to the Moon. But it gets worse. The magnetic fields around magnetars are so intense that they actually affect the structure of space itself. They create what physicists call birefringence in the vacuum, where the emptiness of space starts to behave differently in different directions because the magnetic field is literally warping the quantum foam of the vacuum. And occasionally, magnetars have what are called starquakes, where the solid crust of the neutron star suddenly cracks and shifts, releasing enormous bursts of energy. In 2004, a magnetar called SGR 1806-20 released a burst of energy that, in a tenth of a second, released more energy than the Sun releases in 100,000 years. And this happened at a distance of 50,000 light-years from Earth. If that starquake had happened to a magnetar just 10 light-years away, it would have caused a mass extinction event on Earth. Take a moment to consider the implications. There are objects out there in the universe that, simply by existing and occasionally shrugging their shoulders, so to speak, could wipe out all life on Earth from a distance of 10 light-years. And there's nothing we could do about it. No warning, no defense. Just sudden exposure to a wave of radiation powerful enough to strip away our atmosphere. Doesn't that change how you think about our place in the universe? We tend to think of Earth as safe, as home, as a place sheltered from the harshness of space. But the truth is that we exist in a cosmic shooting gallery, surrounded by objects so powerful and so strange that we're only just beginning to understand them. And speaking of objects we're only beginning to understand, let's talk about quasars. In the early 1960s, astronomers discovered radio sources in the sky that appeared to be stars, but were emitting far too much radio energy to be normal stars. They called them quasi-stellar radio sources, later shortened to quasars, and for a while, nobody could figure out what they were. When astronomers finally measured the distances to these objects using the redshift of their light, they made a shocking discovery. Quasars weren't nearby stars at all. They were among the most distant objects in the universe, billions of light-years away. And if they were that far away and still appeared as bright as they did, they had to be emitting absolutely staggering amounts of energy. A typical quasar emits 1,000 times more energy than the entire Milky Way galaxy, which contains hundreds of billions of stars. Let me repeat that. A single quasar can outshine 1,000 galaxies. How is that possible? What could possibly produce that much energy? The answer turned out to be supermassive black holes. A quasar is what you get when a supermassive black hole, millions or billions of times more massive than the Sun, actively feeds on matter. As gas and dust spiral into the black hole, forming an accretion disk, friction heats the material to millions of degrees. The superheated matter blazes with radiation across the entire electromagnetic spectrum, from radio waves to X-rays. Powerful magnetic fields channel some of this material into jets that shoot out from the poles of the black hole at nearly the speed of light, extending for thousands of light-years into space. These jets are visible in radio telescopes, and they're absolutely enormous. Some quasar jets extend for millions of light-years, spanning distances greater than the separation between the Milky Way and Andromeda galaxies. Imagine that, a jet of matter and energy, powered by a black hole, stretching across millions of light-years of space, blazing with the energy of 1,000 galaxies. But here's what makes quasars especially strange. They're all far away. Very far away. The nearest quasars are billions of light-years distant, which means when we look at them, we're looking billions of years into the past, thanks to the time it takes light to travel across the universe. There are no quasars nearby. There are no quasars in the recent history of the universe. Quasars were common in the early universe, when galaxies were still forming and merging, when supermassive black holes had abundant fuel to feed on. But as the universe aged and settled down, quasars became rare. What this means is that when we observe quasars, we're not just looking at strange objects, we're looking back in time to a more violent and chaotic era of cosmic history. We're seeing what the universe was like when it was young and wild. And there's something haunting about that, isn't there? The idea that the universe had an adolescence, a period of development that was fundamentally different from the mature cosmos we inhabit now. And here's a question to ponder. The supermassive black holes that powered quasars are still out there. Our own Milky Way's central black hole once might have been a quasar billions of years ago. Right now it's quiet, barely feeding, practically dormant. But what would happen if something changed? What if our galaxy collided with another galaxy? as it will in about 4 billion years when the Milky Way and Andromeda merge. Could Sagittarius A star roar back to life as a quasar? And if it did, what would that mean for any life in the galaxy at the time? These aren't idle questions. They touch on fundamental issues about the habitability of the universe, about where and when life can safely exist. Maybe there are periods in a galaxy's life when it's too active, too energetic, too bathed in radiation for complex life to develop. Maybe we're lucky to live in a time and place where our galaxy's central monster is sleeping quietly. But let's shift our attention to something even more mysterious, something that makes up most of the universe yet remains almost completely unknown: dark matter and dark energy. These aren't strange objects in the sense that we can point to them and observe them directly. In fact, we can't observe them directly at all. We only know they exist because of their effects on things we can see. Here's the problem that led to the discovery of dark matter. When astronomers measure how fast galaxies rotate, they find something that doesn't make sense. The stars in the outer parts of galaxies are orbiting the galactic center so fast that they should fly off into space. The gravity from all the visible matter in the galaxy, all the stars and gas and dust we can see, isn't nearly strong enough to hold these fast-moving stars in orbit. It's like watching a car go around a curve at twice the speed it should be able to without skidding off the road. Something's wrong. The solution that physicists have arrived at is that there must be additional matter in galaxies, matter that we can't see because it doesn't emit or absorb light. They call it dark matter, and calculations suggest that there's about 5 times more dark matter in the universe than ordinary matter. Let that sink in. Everything you can see, every star, every galaxy, every nebula, all the planets and asteroids and comets, all of it makes up only about 17% of the matter in the universe. The other 83% is made of something we can't directly detect. What is dark matter? We don't know. It's not ordinary matter that just happens to be dark. It can't be. We've done the calculations, and there simply isn't enough ordinary matter in the universe to account for the effects we observe. Dark matter has to be made of something else, some particle or particles that don't interact with light, that pass through ordinary matter like ghosts. Physicists have proposed various candidates for what dark matter might be. WIMPs, or weakly interacting massive particles, are one possibility. Axions, hypothetical particles much lighter than electrons, are another. Or maybe dark matter is made of primordial black holes that formed in the very early universe. Or maybe it's something else entirely, something we haven't even thought of yet. What's particularly unnerving about dark matter is that it's all around us. The Earth is constantly passing through a stream of dark matter particles. They're passing through you right now as you listen to this. Billions of dark matter particles are zipping through your body every second, and you can't feel them because they barely interact with ordinary matter at all. They pass through the entire Earth like it's not even there, invisible, intangible, yet undeniably real because of the gravitational effects we observe. Doesn't that make you feel a bit strange? To know that there's an entire realm of particles and matter flowing through you and through the Earth that you can't perceive in any way. It's like discovering that you've been living your entire life in a house filled with ghosts that you can't see or hear or touch, but that you know are there because occasionally they move the furniture. But dark matter, as mysterious as it is nothing compared to dark energy. If dark matter is strange, dark energy is downright disturbing because it suggests that something is fundamentally wrong with our understanding of reality. Here's the story. In the 1990s, astronomers were using supernovae, exploding stars, to measure the expansion rate of the universe. They expected to find that the expansion of the universe was slowing down over time, because gravity should be pulling everything back together. What they found instead was shocking. The expansion of the universe isn't slowing down, it's speeding up. The universe is expanding faster and faster, accelerating like a car with the gas pedal pressed to the floor. This shouldn't be possible. Gravity is attractive. It should slow down expansion, not speed it up. But the observations were clear. Something is pushing the universe apart, something that acts like anti-gravity on cosmic scales. They called this mysterious something dark energy, and the calculations suggest that it makes up about 68% of all the energy in the universe. Think about what this means. Dark energy makes up roughly 68% of the universe. Dark matter makes up about 27%. Ordinary matter, the stuff we're made of, the stuff we can see and touch and study, makes up only about 5% of the universe. 95% of the universe is made of things we don't understand. What is dark energy? The honest answer is that we have no idea. One possibility is that it's a property of space itself, that empty space has some inherent energy that causes it to expand. This is related to something called the cosmological constant that Einstein introduced in his equations and later called his biggest blunder, though it turns out he might have been onto something after all. Another possibility is that dark energy is a field that permeates space, something like the Higgs field but different. Or maybe our understanding of gravity is wrong on very large scales, and what we're interpreting as dark energy is actually a sign that Einstein's general relativity needs to be modified. The implications of dark energy are profound and, frankly, a bit terrifying. If dark energy continues to accelerate the expansion of the universe, which is what current observations suggest, then eventually the universe will experience what physicists call the Big Rip. In this scenario, the expansion of space accelerates so much that it eventually overcomes all other forces. First, galaxy clusters are torn apart. Then individual galaxies are shredded. Then solar systems disintegrate. Eventually, even atoms are ripped apart as space itself expands faster than the forces holding matter together can resist. This won't happen for billions, perhaps trillions of years, but still, the idea that the universe has a built-in self-destruct mechanism, that reality itself might be torn apart by some mysterious force we don't understand, is deeply unsettling. We think of the universe as eternal, as the stage on which everything happens, but it turns out the stage itself might be temporary. Now let me tell you about objects that seem to violate our basic assumptions about how planets should behave. Rogue planets. When you think of a planet, you probably think of something orbiting a star, like the planets in our solar system orbit the sun. But scattered throughout the galaxy are planets that don't orbit any star at all. They drift through interstellar space, alone in the darkness, frozen and lifeless, wandering the galaxy for billions of years. How do rogue planets form? There are a few possibilities. Some might have formed around stars, but were ejected from their solar systems by gravitational interactions with other planets or passing stars. Imagine Jupiter-sized planets playing gravitational billiards with each other. And occasionally one gets hit just right and is flung out of the solar system at escape velocity, doomed to wander the galaxy forever. Other rogue planets might have formed independently in interstellar space, condensing from clouds of gas and dust that never quite gathered enough material to form a star. Here's what's disturbing. There might be more rogue planets than there are stars. Some estimates suggest there could be billions or even trillions of rogue planets wandering the Milky Way. Think about that. For every star you can see in the night sky, there might be hundreds or thousands of planets drifting through the darkness between stars, forever isolated, forever frozen. And here's an even stranger thought. Could any of these rogue planets support life? It sounds impossible. Without a star to provide warmth and light, how could life survive? But some scientists have speculated that a large rogue planet, maybe several times the mass of Earth, might retain enough internal heat from its formation and from radioactive decay to maintain liquid water beneath a thick layer of ice. In the crushing darkness beneath the ice, in waters warmed by volcanic vents, could life exist? Could there be biospheres on rogue planets, entire ecosystems evolving in complete isolation, never even knowing that stars exist? It's pure speculation, of course, but it's speculation based on what we've learned about life on Earth. We've discovered life in the deepest parts of the ocean, in places where sunlight never reaches, living off chemical energy from volcanic vents. If life can do that on Earth, why not on a rogue planet? And if rogue planets can support life, then the question of where life might exist in the universe becomes even more complicated. We've been searching for life on planets orbiting other stars, But maybe we should also be thinking about the countless worlds drifting between the stars, invisible and overlooked. Speaking of things moving through space in unusual ways, let me tell you about hypervelocity stars. These are stars that are moving so fast that they're escaping the Milky Way galaxy entirely. Normal stars in the galaxy orbit the galactic center at speeds of a few hundred kilometers per second. Hypervelocity stars are traveling at speeds in excess of 1,000 kilometers per second, fast enough to break free from the galaxy's gravity and head out into intergalactic space. How does a star reach such incredible speeds? The most likely explanation involves the supermassive black hole at the center of our galaxy. Here's the scenario. Imagine a binary star system, two stars orbiting each other, that wanders too close to the central black hole. The intense gravity of the black hole can rip the binary apart, capturing one star while flinging the other away at enormous speed, like a gravitational slingshot. The ejected star becomes a hypervelocity star, shot out of the galaxy like a bullet. These stars are traveling so fast that they'll eventually leave the Milky Way completely, heading out into the void between galaxies. And here's something to think about. If our sun were suddenly turned into a hypervelocity star, if some cosmic event flung our entire solar system out of the galaxy at 1,000 kilometers per second, what would happen to us? Well, the night sky would gradually change. The stars would become fewer and more distant as we moved away from the galactic disk. Eventually, over millions of years, the Milky Way would shrink to a distant spiral of light, and we'd be surrounded by darkness, with only the faint lights of other distant galaxies visible in the sky. Life on Earth could continue, at least for a while. The sun would keep shining, providing warmth and light. But humanity would have to come to terms with being utterly alone, cast out from the galaxy, heading into the infinite emptiness of intergalactic space with no possibility of ever returning. It's a deeply isolating thought, and it makes you appreciate the fact that we live in a relatively stable solar system in a relatively calm part of the galaxy. But speaking of isolation and emptiness, let me introduce you to one of the strangest structures in the universe, the Boötes Void. Remember when I mentioned at the beginning that there's a place where if you put the Milky Way at its center, you'd see nothing for 330 million light-years in any direction? This is that place. The Boötes Void is a region of space that's almost completely empty of galaxies. It's a sphere roughly 330 million light-years in diameter, and it contains only about 60 galaxies. To put that in perspective, a typical region of space that size would contain about 2,000 galaxies. The Boötes Void is astonishingly, unnaturally empty. How did it form? We're not entirely sure. The current theory is that it's a natural consequence of the large-scale structure of the universe. You see, matter in the universe isn't distributed evenly. It's organized into a cosmic web, with galaxies clustered along filaments and sheets, and vast empty regions, called voids, between them. The Boötes Void is just an unusually large void, perhaps formed by the confluence of several smaller voids merging together. But there's something profoundly unsettling about the idea of such emptiness existing on such a large scale. If you could somehow travel to the center of the Boötes Void and look around, you would see almost nothing. A few faint, distant smudges of light that are the handful of galaxies within the void, and far, far away, the faint glow of galaxy clusters on the void's edge. But mostly, you'd see darkness. Empty space stretching in all directions for hundreds of millions of light-years. Imagine being an intelligent civilization that evolved on a planet in a galaxy in the center of the Boötes Void. What would your understanding of the universe be? You'd see almost no other galaxies. You might not even realize that the universe was full of galaxies at all. Your entire cosmology would be fundamentally different from ours. You might think you lived in a small, lonely universe with only a handful of galaxies in it. It's a reminder that our perspective on the cosmos is shaped by where we happen to be located, and there might be things about the universe that we don't understand simply because we don't have the right vantage point. And speaking of things we don't understand, let's talk about fast radio bursts, or FRBs. These are one of the most recent additions to the list of cosmic mysteries, first discovered in 2007, and they're exactly what they sound like, extremely bright bursts of radio waves that last only a few milliseconds. Here's what makes FRBs so strange. They're incredibly powerful, releasing as much energy in a few milliseconds as the sun releases in several days. They come from billions of light years away, from distant galaxies. And until recently, we had no idea what was causing them. When FRBs were first discovered, there was a brief moment of excitement and speculation. Could they be signals from alien civilizations? The bursts were so powerful and so brief that it seemed like they might be artificial, like cosmic beacons or transmission beams from some advanced technology. But as we detected more and more FRBs and studied their properties, the alien hypothesis became less and less likely. The current leading theory is that FRBs are caused by magnetars, those ultramagnetic neutron stars I mentioned earlier. The idea is that starquakes or other violent events on magnetars can release sudden bursts of radio energy. In 2020, astronomers detected an FRB coming from within our own galaxy, and they were able to trace it to a known magnetar, providing strong evidence for this theory. But not all FRBs fit neatly into the magnetar explanation. Some FRBs repeat, flashing over and over again from the same location in space. Others happen only once and are never seen again. Some FRBs have properties that are hard to explain with any current model. The truth is, we're still figuring out what FRBs are and what causes them, and there might be multiple different types of events that all produce similar-looking bursts. What's exciting about FRBs is that they're a new window into the universe. They happen all the time, thousands of them every day across the entire sky, and each one carries information about the space it traveled through on its way to Earth. By studying FRBs, we can learn about the intergalactic medium, the tenuous gas that fills the space between galaxies. We can map out the distribution of matter in the universe. We might even be able to use FRBs to test fundamental physics in extreme conditions we can't recreate on Earth. But there's also something slightly eerie about FRBs. The universe is constantly screaming at us in radio waves, thousands of times a day, these powerful blasts of energy from distant galaxies, and until very recently we had no idea it was happening. It makes you wonder what else is out there that we're not detecting because we're not looking in the right way or at the right wavelength. Now, let me tell you about an object that captured public imagination like few others. Tabby's star, also known as KIC 8462852. This is a star about 1,400 light-years away from Earth, and for a while, it was at the center of the most exciting alien megastructure hypothesis in recent memory. Here's what happened. The Kepler Space Telescope, which was designed to find planets by detecting the tiny dip in a star's brightness when a planet passes in front of it, noticed something very strange about Tabby's star. The star was dimming, but not in a regular, predictable way like you'd expect from an orbiting planet. Instead, it showed irregular, dramatic dips in brightness, sometimes dimming by up to 20%. No known planet could block that much light. A planet the size of Jupiter only blocks about 1% of its star's light. Scientists scrambled to explain what could be causing such dramatic, irregular dimming. Comets. A swarm of comets breaking up and creating a debris cloud could potentially explain some of the observations, but it seemed unlikely. A circumstellar disk. But Tabby's star is too old to still have a disk. What else could it be? And then someone suggested something that made headlines around the world. What if the dimming was caused by an alien megastructure? Specifically, what if an advanced civilization had built a Dyson swarm around the star, a collection of orbiting solar panels or habitats designed to capture the star's energy? Such a structure could potentially cause irregular dimming as the components of the swarm moved around the star. For a brief, glorious moment, it seemed possible that we might be detecting evidence of a highly advanced alien civilization, one capable of megascale engineering projects. The SETI Institute even pointed radio telescopes at Tabby's star, listening for signals. But they found nothing unusual. More observations and analysis eventually led to a more mundane explanation. It appears that Tabby's star's dimming is most likely caused by dust, possibly from a cloud of dust that the star is passing through, or from dust produced by the breakup of a planet or large asteroid in the star system. The pattern of dimming at different wavelengths of light is consistent with dust, not with an opaque megastructure. So, no aliens. Probably. But the episode raises interesting questions. How would we recognize an alien megastructure if we saw one? What would be the telltale signs? And more broadly, if there are advanced civilizations out there in the galaxy, why haven't we seen clear evidence of them yet? This is the famous Fermi paradox. The universe is vast and old, and even with slower-than-light travel, a sufficiently motivated civilization could colonize the entire galaxy in a few tens of millions of years. So where is everyone? Maybe they don't exist. Maybe intelligent life is incredibly rare, and we're alone or nearly alone in the galaxy. Maybe intelligent civilizations tend to destroy themselves before they become capable of interstellar travel. Maybe they exist but are deliberately staying quiet, observing a sort of cosmic non-interference policy. Or maybe they're out there, but we're not recognizing the signs because we don't know what to look for. Tabby's star reminds us that the universe is full of phenomena we don't yet understand, and we shouldn't be too quick to jump to conclusions, either mundane or extraordinary. As Carl Sagan famously said, extraordinary claims require extraordinary evidence. But we should also keep our minds open to the possibility that the universe might surprise us in ways we can't currently imagine. Speaking of surprises, in 2017, astronomers discovered something unprecedented: an interstellar object passing through our solar system. They named it Oumuamua, a Hawaiian word meaning scout or messenger from afar, and it was unlike anything we'd seen before. Oumuamua was the first confirmed object from another star system ever detected passing through our solar system. Think about what that means. This object formed around another star, possibly billions of years ago, was somehow ejected from its home system, and has been drifting through interstellar space ever since, until by chance its path intersected with our solar system and we happened to spot it as it swung around the sun and headed back out into the darkness. But Oumuamua was strange in ways that went beyond just being an interstellar visitor. Its shape was highly unusual, very elongated, probably at least 5 to 10 times longer than it was wide, making it look more like a cigar or a needle than the roughly spherical shapes of most asteroids and comets. It was tumbling through space, rotating every 7 hours or so. And it didn't show any signs of outgassing, no tail, no coma of gas and dust, which was odd because it passed close enough to the sun that any ices should have vaporized. And then there was the acceleration anomaly. As Oumuamua was leaving the solar system, astronomers noticed it was accelerating slightly, moving faster than it should be based solely on the sun's gravity. With a comet, this wouldn't be surprising. Outgassing from the sun's heat creates a tiny rocket effect that can change a comet's trajectory. But Oumuamua wasn't showing any visible outgassing. So what was causing the acceleration? One possibility is that Oumuamua was outgassing, but in a way we couldn't detect, perhaps venting pure hydrogen that would be invisible to our telescopes. Another possibility is that radiation pressure from sunlight was pushing on it. Oumuamua is small enough and possibly thin enough that radiation pressure could have a noticeable effect. But then Avi Loeb, a respected astronomer from Harvard, suggested something that made headlines. What if Oumuamua was artificial? What if it was a probe or a light sail created by an alien civilization? A light sail, a large, thin reflective sheet designed to be pushed by starlight, could explain both the unusual elongated shape and the acceleration anomaly. Most scientists are skeptical of this hypothesis. There's no evidence that Oumuamua is artificial, and there are natural explanations that can account for its properties, even if those explanations require some unusual assumptions. But Loeb's suggestion highlights an important point. We should be open to the possibility that we might someday detect evidence of alien technology, and we need to think seriously about what that evidence might look like. Oumuamua has already left the solar system, moving at about 26 kilometers per second, heading out into interstellar space. We'll never see it again. We didn't get a good look at it while it was here because it was discovered only after it had already passed its closest approach to the Sun. If another interstellar object passes through the solar system, and astronomers think they probably do fairly regularly, we'll be better prepared. We'll point more telescopes at it. We'll gather more data. Maybe we'll even try to send a spacecraft to intercept it and get a close-up look. But for now, Oumuamua remains a mystery, a visitor from another star system that raised more questions than it answered. And that, in many ways, is the nature of science. Every answer leads to new questions. Every discovery reveals new mysteries. Now let me take you into the realm of theoretical objects, things that might exist according to our understanding of physics, but that we've never actually observed. These objects exist in the strange borderland between science and speculation, things that the math says should be possible, but that nature might or might not actually create. First, consider white holes. If black holes are regions of spacetime where gravity is so strong that nothing can escape, white holes would be the opposite. Regions of spacetime where nothing can enter. A white hole would spew matter and energy outward, the time reverse of a black hole swallowing everything. The equations of general relativity that predict black holes also predict white holes. Mathematically, they're equally valid solutions. But physically, white holes are deeply problematic. For one thing, they would violate the second law of thermodynamics, which says that entropy, disorder, always increases over time. A white hole would represent a region of decreasing entropy, which shouldn't be possible. For another, white holes would be incredibly unstable. Even a single photon falling toward a white hole from the outside could cause it to collapse. Most physicists think white holes probably don't exist in nature, but there's been some speculation that they might be connected to black holes, that what goes into a black hole might come out of a white hole, possibly in another universe or another region of spacetime. This is pure speculation, untestable with current technology, but it's an idea that captures the imagination. Then there are cosmic strings, hypothetical one-dimensional defects in spacetime left over from the very early universe. Imagine when the universe was a fraction of a second old, cooling rapidly after the Big Bang. As it cooled, it might have undergone phase transitions, similar to how water freezes into ice. During these phase transitions, defects might have formed, similar to the cracks that form in ice as it freezes. But these wouldn't be cracks in matter, they would be cracks in spacetime itself. A cosmic string would be incredibly thin, much thinner than an atom, but incredibly dense. A piece of cosmic string just a few kilometers long would have the mass of the Earth. And cosmic strings would have bizarre gravitational effects. A cosmic string wouldn't attract objects to it the way normal matter does. Instead, spacetime around a cosmic string would be flat but with a wedge cut out like a slice removed from a pizza. If you traveled around a cosmic string and returned to your starting point, you'd find that you hadn't quite made a complete circle. You'd be missing a few degrees. Light passing near a cosmic string would create double images of objects behind it. Do cosmic strings exist? We don't know. We've never detected one. But if they do exist, they would be relics from the very birth of the universe. Fossils from a time when the cosmos was unimaginably hot and dense. Finding a cosmic string would open a window into physics at energy scales we could never recreate in particle accelerators, giving us insight into the fundamental nature of reality itself. And then there are strange stars, also called strange matter stars or quark stars. These are hypothetical objects that might be even denser than neutron stars. In a neutron star, protons and electrons are crushed together into neutrons. But if the pressure gets high enough, maybe in the cores of the most massive neutron stars, the neutrons themselves might break down into their constituent quarks. Normal matter is made of protons and neutrons, which are themselves made of quarks held together by the strong nuclear force. But under extreme pressure, it might be possible for quarks to exist in a new state called strange quark matter, where up quarks, down quarks, and strange quarks all mix together in a soup. And here's where it gets weird. Some theories suggest that strange quark matter might actually be more stable than normal matter. If that's true, If strange quark matter is truly the most stable form of matter, then it has disturbing implications. Strange quark matter might be infectious. If a piece of strange quark matter touches normal matter, it might convert that normal matter into strange quark matter, releasing energy in the process. The newly converted strange matter could then convert more normal matter in a chain reaction. In theory, a single piece of strange quark matter, may be created in the collision of two neutron stars, could fall to Earth and convert the entire planet into a lump of strange matter in a matter of minutes. The Earth wouldn't explode or be destroyed, it would simply be transformed, rearranged at the nuclear level into a much denser, much smaller sphere of strange quark matter. Now, before you panic, let me emphasize that this is highly speculative. We don't know if strange quark matter exists. We don't know if it's more stable than normal matter. And even if it is, there are good reasons to think that it wouldn't necessarily be infectious to normal matter under normal conditions. Physicists have thought about these scenarios extensively, especially in the context of particle collider experiments that create conditions of extreme energy and pressure. The consensus is that we're almost certainly safe. But almost certainly isn't quite the same as definitely, is it? And that tiny sliver of uncertainty, the acknowledgement that our theories might be incomplete, that nature might surprise us, is part of what makes physics both exciting and slightly terrifying. Consider another theoretical object, the Thorne-Zitko object, predicted by physicists Kip Thorne and Anna Zitko in the 1970s. This would be a neutron star inside a red giant star, a stellar hybrid unlike anything else in the cosmos. How could such a thing form? Imagine a binary star system where one star goes supernova and leaves behind a neutron star. Over time, the neutron star and its companion star spiral closer together, until eventually the neutron star plunges into the outer layers of the companion star. Instead of merging completely, the neutron star settles into the core of the larger star, replacing its normal fusion core with an incredibly dense neutron star core. From the outside, a Thorne-Zitko object would look like a slightly unusual red giant star. But inside, it would be completely different. The energy driving the star wouldn't come from normal fusion, but from matter falling onto the neutron star core and releasing gravitational energy. This would create unusual chemical signatures, elements, and isotopes that wouldn't normally be produced in a red giant. In 2014, astronomers announced that they might have found a Thorne-Zitko object, a red giant star with unusual chemical abundances consistent with having a neutron star core. But the evidence is not conclusive, and it's possible that the unusual chemistry has another explanation. We need more observations, more data, to know for sure. What I want you to take away from this discussion of theoretical objects is that the universe is strange enough that the objects we can see and study are probably just a fraction of what's possible. The laws of physics allow for the existence of things that seem like they shouldn't be real, things so bizarre that until we have solid observational evidence, even physicists are skeptical. And yet, the history of astronomy is full of examples where things that were once thought to be purely theoretical turned out to be real. Neutron stars were predicted theoretically decades before they were discovered as pulsars. Black holes were solutions to Einstein's equations for decades before we had evidence they actually existed. Who knows what other theoretical objects might turn out to be real? So what does all of this mean? What should we take away from this journey through the strangest objects in the universe? First, it means that reality is far, far stranger than our everyday experience would suggest. The universe we live in is not the comfortable, predictable place we often imagine it to be. It's a place where matter can be crushed to infinite density, where space itself can be torn apart, where objects exist that we can't see or touch but that outweigh everything we can see by a factor of 5 to 1. It's a place where the fundamental nature of most of the universe is a complete mystery to us. Second, it means that we're still, in many ways, at the beginning of our exploration of the cosmos. We've learned an incredible amount in the past century, but every discovery reveals new questions, new mysteries. We don't know what dark matter is. We don't know what dark energy is. We don't know if there's life elsewhere in the universe. We don't know what happens inside a black hole. We don't know if the theoretical objects predicted by our equations actually exist in nature. There is so much we don't know, and that should be both humbling and exciting. Third, it means that the universe doesn't care about our intuitions or our comfort. The universe is under no obligation to make sense to us. Things exist that violate our common sense, that seem impossible, that make us uncomfortable. And yet they're real. The fact that something seems weird or counterintuitive or disturbing doesn't make it any less real. We have to adjust our understanding to match reality, not the other way around. But there's also something profoundly hopeful in all of this strangeness. Every mystery we've encountered, from the nature of stars to the expansion of the universe, has eventually yielded to patient observation and careful thought. We don't understand dark matter yet, but we're working on it, building more sensitive detectors, proposing new theories, gathering more data. We don't fully understand black holes, but we're making progress, taking pictures of them, studying the gravitational waves they produce when they collide, developing better mathematical models. Science is a process of turning the unknown into the known, of pushing back the boundaries of ignorance. And yes, every time we answer a question, new questions emerge. The boundary of our knowledge expands, but so does the boundary of our ignorance, because we become aware of new things we don't understand. But this is progress. This is growth. This is how we learn. Think about the fact that 100 years ago, we didn't know that other galaxies existed. We thought the Milky Way was the entire universe. We didn't know about black holes or neutron stars. We didn't know that the universe was expanding. We didn't know about dark matter or dark energy. All of this is knowledge we've gained in just the last century, in the blink of an eye on cosmic timescales. What will we know 100 years from now? What strange objects will future astronomers discover? What mysteries will they solve? What new mysteries will they uncover? Maybe we'll detect dark matter particles directly in laboratories here on Earth, and we'll finally understand what makes up most of the matter in the universe. Maybe we'll develop a theory of quantum gravity that explains what happens at the singularity inside a black hole. Maybe we'll discover that life is common in the universe, that we're surrounded by biospheres on moons and planets and rogue worlds throughout the galaxy. Or maybe we'll discover that we're alone, that Earth is a precious rarity, that the emergence of intelligent life requires such a specific and unlikely set of circumstances that it's happened only once in our galaxy or even in the observable universe. Maybe we'll detect signals from an alien civilization, or find artifacts of a long-dead spacefaring species, or discover a Dyson swarm around a distant star. Or maybe we'll find that the universe is silent, that we're the first civilization in our corner of the cosmos to reach for the stars. We don't know. We can't know, not yet. But we can keep looking. We can keep building better telescopes and more sensitive detectors. We can keep asking questions and testing hypotheses. We can keep pushing the boundaries of what we know and what we can know. And in the meantime, we can stand in awe of the universe we find ourselves in. We can appreciate the beauty and the strangeness of a cosmos filled with objects that challenge our understanding and our imagination. We can feel the thrill of knowing that we're living in a time of unprecedented discovery, when new revelations about the nature of reality are emerging year after year. The night sky is no longer just a pretty backdrop for our lives. It's a window into a universe of wonders and terrors, of mysteries and revelations. Every point of light you see when you look up represents a massive sphere of fusing hydrogen, a sun in its own right, possibly with planets orbiting it, possibly with life evolving in alien oceans or alien atmospheres. Between those points of light, invisible to your eyes, are objects stranger than you can imagine. Black holes tearing space-time itself, neutron stars spinning hundreds of times per second, dark matter flowing through you like a cosmic wind, dark energy pushing the universe apart. And you, standing on this small blue planet, made of atoms forged in the hearts of ancient stars, are part of it all. You are the universe looking at itself, matter organized in such a way that it can contemplate its own existence and wonder about its own nature. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of it was created in stars that lived and died before the sun was born. You are, in a very literal sense, made of star stuff, as Carl Sagan so eloquently put it. The strangest objects in the universe aren't just out there in the distant cosmos. In a sense, you're one of them. You're a collection of atoms arranged in a configuration so complex that it gives rise to consciousness, to self-awareness, to the ability to understand, at least partially, the universe you're part of. The odds against your existence are astronomical. The specific atoms that make up your body had to come together in exactly the right way. Your ancestors had to survive long enough to reproduce, going back through millions of generations, through all the mass extinctions and climate changes and cosmic near misses that Earth has experienced. The planet you live on had to form at exactly the right distance from the sun, with exactly the right mix of elements. The sun had to be the right kind of star, stable and long-lived. The universe had to have the right fundamental constants, the right laws of physics, to allow for the existence of stars and planets and life. Change any of these factors even slightly, and you wouldn't exist. None of us would. The fact that we're here at all, able to contemplate the strange and wonderful universe we inhabit, is itself perhaps the strangest thing of all. So the next time you look up at the night sky, remember what you're looking at. You're not just seeing points of light on a dark background. You're seeing across distances so vast that the light from those stars has been traveling for years or decades or centuries to reach your eyes. You're looking back in time, seeing stars as they were when that light began its journey, not as they are now. You're seeing a universe filled with objects so strange that they challenge the very limits of human understanding. You're seeing a cosmos that is vast beyond comprehension, ancient beyond imagining, and stranger than we can fully grasp. And yet, for all its strangeness, for all its mysteries, the universe is knowable, at least in part. We can study it. We can understand it. We can piece together the story of how it came to be and how it works. We can stand on this small planet and reach out with our minds and our instruments to touch the furthest reaches of space and time. That's the real wonder. Not just that the universe is strange, but that we can understand it. Not just that black holes and neutron stars and dark matter exist, but that we, fragile beings made of star stuff, living on a thin layer of rock and water orbiting an ordinary star, can discover them and study them and begin to comprehend them. We are, as far as we know, the universe's way of understanding itself. We are how the cosmos comes to know its own nature. And if that's not a profound and humbling thought, I don't know what is. The strangest objects in the universe aren't just subjects of scientific study. They're reminders of how much there is still to discover, how much we still don't understand, how vast and mysterious and wonderful the reality we inhabit truly is. They're invitations to keep looking, keep questioning, keep exploring. They're challenges to our understanding and our imagination. Every strange object we've discussed, from black holes to rogue planets to dark matter, represents a frontier of human knowledge, a place where our understanding gives way to mystery. And every one of them is an opportunity to push that frontier a little further, to expand the circle of human knowledge, to turn mystery into understanding. But some mysteries may never be fully solved. Some questions may be fundamentally unanswerable. And that's okay. The universe doesn't owe us answers. The fact that there are mysteries, that there are things we may never fully understand, makes the cosmos more interesting, not less. It means there will always be new questions to ask, new phenomena to study, new wonders to discover. As we've journeyed through the strangest objects in the universe, from the crushing gravity of black holes to the invisible dominance of dark energy, from the diamond-hard surfaces of neutron stars to the incomprehensible emptiness of the Boötes void, we've seen that the universe is far stranger and more wonderful than our ancestors ever imagined. They looked up at the night sky and saw gods and heroes written in the stars. We look up and see something even more extraordinary. A universe governed by comprehensible laws, yet full of objects and phenomena that push those laws to their limits and beyond. We've seen objects that represent the extremes of physical reality. The hottest temperatures, the strongest magnetic fields, the highest densities, the greatest emptiness. We've encountered things that exist at the edge of what physics allows, and things that might exist beyond that edge, in the realm of speculation and theory. And through it all, one theme has emerged. The universe is under no obligation to match our intuitions or our expectations. It is what it is, regardless of whether it makes sense to us. Our job, as conscious beings capable of understanding, is not to impose our preconceptions on the universe, but to observe it carefully, to think about it rigorously, and to adjust our understanding to match what we actually see, no matter how strange that might be. The strangest objects in the universe are strange not because they're somehow separate from natural law, but because they represent nature pushed to extremes we don't encounter in our everyday lives. They're what happens when gravity becomes strong enough to trap light, when matter is compressed to nuclear densities, when magnetic fields become powerful enough to warp quantum fields. They're the universe showing us what's possible when the dials are turned all the way up. And here's the most exciting part. We're still discovering new strange objects. Fast radio bursts were unknown just a couple of decades ago. The first interstellar object passing through our solar system was detected only a few years ago. Who knows what else is out there, waiting to be discovered? What other strange objects exist that we haven't found yet because we're not looking in the right place or in the right way? Maybe there are objects out there stranger than anything we've discussed. Maybe there are phenomena that we haven't even thought to look for. Maybe the universe has more surprises in store for us, things that will revolutionize our understanding of physics and reality just as the discovery of black holes and dark matter did. Or maybe we've found most of the truly strange things already, and future discoveries will be refinements of what we already know rather than revolutionary new phenomena. We can't know until we look. But this much is certain. The universe will continue to surprise us. It always has. Every generation of astronomers and physicists has discovered things that the previous generation didn't expect, didn't predict, couldn't have imagined. There's no reason to think that our generation will be the last to be surprised. So keep looking up. Keep asking questions. Keep wondering about the strange and marvelous universe we inhabit. Because the strangest objects in the universe aren't just out there in the distant cosmos. They're part of the story of reality itself, part of the grand tapestry of existence that we're all woven into.